All right, we're in 9.1, Part 1, trying to do some actual reflections. We're going to use our geometer. Here's a little basics. You see right here it says the reflection of point A over line L. Here's line L, the line we want to reflect over. Here's point A. Well, if we want to reflect that over, you know, it's like there's no way that A is going to go over here. That doesn't work. A prime, or I should say A prime. A prime is not going to go down here. Isn't A prime going to end up going like straight across the line? To where if I was to connect this little imaginary segment and call this like segment A prime right here, you know, this guy right here is totally perpendicular to that line. It makes a right angle. And that distance, you know, like from here to here, boom, is the same as the distance from right there. So we could put those tick marks on there. And this is the definition of reflection, guys, to where these letters are just generic. But if the reflection of some point, in this case it's A, over whatever in the line you're talking about, in this case it's line L, equals A prime, then here it is. L is the perpendicular bisector of that segment that's formed. It's an imaginary segment, but it's the main key is if I mention the definition of reflection, we're going to say something about a perpendicular bisector. So we'll kind of go through that as we go. So to do a reflection, we will need our geometer. And here's what we got to do. We got to take a break from this video. There is another video right in this playlist that shows you how to do a reflection with your geometer. I can't do it with this screen recording program. So if you just kind of pause this, go watch that other video. It's like 2 minutes long, and then come back to this video after you're done. We'll be rocking and rolling. Thank you. Line that out very much longer. The reason why you do that is it keeps your geometer perpendicular with the line you're reflecting over. So we'll do that and reflect A, B, C, D, and F. Go ahead and do them all. So go ahead and pause the video. I've got that done already. Just pause the video and get those 5 points reflected. And then once you've done that, all you have to do is take your straight edge and connect those puppies together. So a lot of pausing until you get this done. And then that brings us to our next part of this question right here, which is the reflection postulate. It says that reflection postulate is sometimes called the ABCD postulate. The reason why it's called the ABCD postulate is because there are 4 things that are preserved by every reflection. They start with the letters A, B, C, and D, so each one of those things starts with this letter. And here's what A stands for. A stands for angle measure. Angle measure. So, measure. I can't spell. Angle measure. What that means is if this original angle right here measured 30 degrees, then if I reflect that angle over here and get this green angle, the green angle should also measure 30 degrees. It's not going to grow or shrink or anything like that. Reflections preserve angle measure. Keeps the measure of that angle exactly the same. B stands for betweenness. Betweenness is preserved by every reflection, meaning in this original picture, point B was between A and C because they're collinear and B is between there. So that means when you reflect them, B prime should be between A prime and C prime. They're not going to jump out of order or anything like that. C stands for collinearity. It's the word collinear with I-T-Y at the end. Collinearity. C stands for collinearity. A, B, and C were collinear points, so A prime, B prime, C prime. If you do a reflection, points won't jump off line or anything like that. And D stands for distance is preserved. So these 4 things are preserved by every reflection. That means if this distance from A to C was 2 inches, then the distance from A prime to C prime will also be 2 inches. It's not going to grow or shrink or anything like that. So reflections preserve angle measure, betweenness, collinearity, and distance. And we'll use a couple of these for justifications as we go along today. So let's keep on rocking. In the picture at the right, what is the orientation of triangle XYZ? Orientation, in our own words, means what way around the clock are the letters going? Like when they call it triangle XYZ, okay, that means start with X since it's the first letter, and just go around the clock XYZ in the order that they tell them. XYZ, from X to Y to Z, going around the clock. Is that clockwise or counterclockwise? Well, that's counterclockwise. Good deal. What would be the orientation of its reflection image? Remember, the beginning guy is the pre-image. You haven't done anything. And if I reflect that puppy over there, well, X would reflect over here. I'm just going to do a rough sketcher to X prime. Y would reflect over here somewhere to y prime, and z would reflect right here to z prime, and I connect them together. And you have to go in the same order. If this went x, y, z, you have to go x prime, y prime, z prime. So if you go around the clock that way, x prime, y prime, z prime, that went clockwise. And what that means is reflections reverse orientation. Reflections reverse, if I could speak today, orientation. Meaning if the original guy's counterclockwise, then its pre-image was clockwise. We can go back and see right here in that first problem that we did with the triangle, if I call it triangle, come on, keep going backwards. If I call this triangle ABC, then triangle ABC, going around in that order, counterclockwise. To go A prime, B prime, C prime, you would go clockwise. So reflections do not preserve orientation. They preserve these four things: angle measured between us, collinearity, and distance. But one thing not preserved is orientation. Number 4, they want me to draw this. The question I have for you is, can you say this out loud? The little r stands for reflection. So they're asking you to draw the reflection of, and then you say the name of this dude, like it's just called ABCDE. Draw the reflection of ABCDE over this line's name, line AB. Draw the reflection of ABCDE over line AB. So we just go one point at a time, A, B, C, D, and E, and we reflect them over this line. Start by, of course, extending that line out very much longer. And first I want to reflect A over that line. Well, since A is on that line, right, it's line AB, you know it's on there, it's not going to move. If you measure how far away it is, it's 0 centimeters away, so you would not move it at all. And B is on that line, so it's not going to move at all. So honestly, all you have to do is reflect C, D, and E, and make sure you label them as you go. When you reflect C over here, don't just put a dot here, then reflect D and put a dot there, and then put E here, and not put their names, because you're going to get very confused when the pictures get more complicated. Once you reflect C, call it C prime right away. Once you reflect D, call it D prime right away. So when you do that, I went ahead and measured things out perfectly, and it'll look like so. Go ahead and pause the video and get that done if you need to. Then you need to connect those dots together, and it gets a little tricky on how to connect things together when there's more than 3 points. So they just go and look at your pre-image here. Since A connected to E, that means A will connect to E prime. And E connects to D, so E prime should connect to D prime. And something screwed up there. So E connects to D prime. D connects to C, so D prime to C prime. And B connects to C, so B prime to C prime. So there, I have reflected A, B, C, D, E over line AB. Number 5, we get a little bit of a problem because everything we've reflected so far has been straight. You know, it's had straight edges. This has got a curve for an edge right here. So what we can do first is all of these cornery type points right here where there's a definite corner, why don't we go ahead and label those just A, B, and C, and extend out line M, and go ahead and pause the video and reflect A, B, and C over that line right away. So go ahead and do that. It'll look like so. And then I connect them together as well. And what you want to do next is, you see on this bad boy right here where this curve kind of starts to max out, like I'm going out, 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 out. Then all of a sudden I start coming back in. So where the curve starts to max out, that's like its vertex type point, I'm going to put a point D right there. And I'm going to take that point D and I'm going to reflect it over that line. So I found the max out point and placed it on there and reflected it over that line. Actually, I called it C on accident. I should have called it D. So D, my bad. And then what you want to do is, once you get over there, then we're just going to do our best freehand ability to kind of connect this together. It's just going to be a rough sketch. So as best you can, I know we're not all artists here, but do some sort of job to connect that back together. And yours might look worse than mine. Hopefully yours looks better than mine, because that looks pretty bad. But just do your best freehand job. If you want to get more accurate, you can place more and more points on this original pre-image right here and connect those together. But that's what we're going to do to deal with the curve stuff. All right. Moving on, number 6 says, draw and label a figure that shows the reflection of RQTS over line C is RWTY. So they want us to start with our own figure. I have a line drawn already. That's where we got to start. You know, it's like the name of the line is C. I did that right here. So we got to start with a line, and you might as well make it a long line since our first step is always to extend that line out very much longer. And people try to make this problem more complicated than it actually is. All they have to do is go one point at a time. According to this reflection statement right here, this point should reflect to that point. So R should reflect to R. Well, there's only one way that R reflects to R. Since it reflects to the same letter, that means R has to be on that line. So I have drawn R on the line somewhere. It doesn't matter where, you know, but just put R on that line somewhere. So I've done that point. Next thing is Q should reflect to W. So what that means is, since those are different letters, that Q has got to be off of the line somewhere. So what do you say we put Q somewhere like right here? Doesn't really matter, but we'll go ahead and put Q right there, and now reflect Q over line C. And when you do that, don't call it Q prime. They want you to call it W. So put a point Q somewhere off the line. It's got to be off the line, and reflect it and call that point W. So I got Q in red, and I got W in blue. Then the next point is T. It reflects to T. So since it reflects to itself, that means it's got to be on the line. So put T on the line somewhere. Doesn't matter where. And then S is the last point. It reflects to Y. That's where you got to be a little bit careful. Okay, you can't just put S anywhere you want to. Like, let's say I decided to put S right here. What you have to end up doing with these, this is a bad place for S, and I'll show you why. What you have to end up doing is this should be some sort of quadrilateral, right? 4 letters in a row means that's a quadrilateral. And if I connect them together, they have to connect in this order: R to Q to T to S. So if you go R to Q to T to S, and then the last letter S has to connect back to R again, when I draw that shape, that's not a polygon, right? Because this segment intersects in more than exactly 2 places, 1, 2, 3. So you got to be careful of where you put S. So what do you say you follow my lead right here, and let's put S like right here somewhere. So I'll put S there, and it reflected to Y. I've drawn that. Now connect those together. So I'm going to connect all my red segments first. This first dude, I'll highlight it red right here. This is the red guy, RQTS. So R to Q, Q to T, T to S, and the last letter goes back to the first letter. I reflected that. Then you got to do your blue dude. So switching colors. Same order. R goes to W, W goes to T, T goes to Y, and Y goes back to R. Are you going to the mall today, Billy? And there we go. I have drawn a figure that shows the reflection of RQTS over line C is RWTY. Here they say use the figure at the right where the reflection of triangle RMG over line GN equals triangle BPG. They say if the measure of angle P is 46 degrees, so I'll go put that into the picture right there, it's 46 degrees, find the measure of angle M. Well, what we do is we actually use this reflection statement right here and see, you know, it's like, okay, here's P and here's M. Would you believe that they like correspond with each other? That means that like angle P would reflect to angle M over that line GN. So since reflections preserve angle measure, the measure of angle M has to be the same as the measure of angle P, so that answer is 46 degrees. In our justification, real simple, reflections preserve angle measure. So we got to write it out like this. That's our deal. That's from the ABCD postulate on the other page. Those 4 things preserve angle measure between this linear distance. Here was the big one. We were talking about angle measure. Here we go. Right here, the next one is so simple. If you just know how to read it, it says if the distance from R to G equals 2,
find the distance from G to B. Well, if we go back and look at the reflection statement, R to G is Mr. First and Last. Does he go with G and B, which is Mr. First and Last? It sure does. Since reflections preserve distance, that guy's got to be the same. For that reason, reflections preserve distance. Pretty simple, this justify, and there's a lot of that, so we got a couple more coming up right here. Here, do you see how they give me a reflection right here? These guys reflect each other. They want to know why the distance from B to C is equal to the distance from Y to Z. Well, here's BC, here's Y to Z. Those correspond with each other, and since we're talking distance, that's reflections preserve distance. So, nice simple thing right there. Here, easiest way, if you know how to say this, you're going to rock it. That's the measure of an angle, like measure of angle CBA is equal to the measure of angle ZYX. We're talking about angle measure. We were given a reflection, so reflections preserve angle measure. Reflections preserve angle measure. And then here, on the next one, they say M, that's the reflecting line, is the perpendicular bisector of segment BY. Dude, if I say perpendicular bisector, you say definition of reflection. That's the first thing that we really talked about on this here video, the definition of reflection. And then here, speaking of that, they say according to the definition of reflection, if the reflection of point Q over line L equals T, then how are L, Q, and T all related? It's kind of a weird question, but here's how it works. The line, in this case his name is L, is the perpendicular bisector of whatever the segment would be out of these two letters. In this case, since it's Q and T, it'd be segment QT. So if I say definition of reflection, you better text me something about a perpendicular bisector. And the line is always the perpendicular bisector of the segment formed by the points that you got reflected right there. So here's a new guy. This little guy's called the figure reflection theorem. A little theorem that we'll use in some justifications. If you reflect any kind of figure, you're going to get back the same type of figure. I hope that makes sense. If I reflect a triangle, I better get a triangle back. If I reflect a segment, I better get a segment back. If I reflect a hippopotamus, I should get a hippopotamus back. So if you see here how they reflected a triangle and got back another triangle, that makes sense. They ask us to justify the following. Here, the reflection of segment TX over that same line should be segment BM. Well, this is not reflections preserve distance because it doesn't mention anything about distance. This doesn't do anything about angle measure, so it's not reflections preserve angle measure. They're reflecting a figure. They're reflecting a segment, and we are getting back the same kind of segment. That's why that is the figure reflection theorem. Figure reflection theorem. And as you can see here, aren't they reflecting an angle, and would you believe they got back an angle again? That is also the figure reflection theorem. It's such a simple thing when you get the hang of it. It's like, oh, duh, if I reflect an angle, I better get an angle back. If I reflect a segment, I better get a segment back. But see, this guy, he is not the figure reflection theorem because it doesn't reflect anything. It says the distance from T to R equals the distance from B to A. They did do a reflection with these triangles, so that's back to the old school, reflections preserve distance. So those are the ABCDs, and this is the D in this category. Reflections preserve distance. So, cool. What a nice little hodgepodge video. Let me know if you guys have questions. Have a good one.